see.
Okay.
On my computer here. I
Yeah.
just bought a $250 100-degree eyepiece, 20mm 100-degree eyepiece from Astronomics, which is they have a new Astrotech eyepiece coming in, and they have a sale on for just $250, and you start looking at the prices for other things. It's amazing.
$1,000 up to.
So here's a Cloudy Nights for a used Explorer Scientific, $550.
Yeah, because it's gone up in price because of the
This supply.
yeah, supply issues.
Let's see, their website, it's $800, and so the one I bought is $250. So I'm hoping that it's fairly good, pretty good for doing outreaches or around the house. It'll see it's a little bit lighter in weight. Doesn't say argon purged or anything, but
Do you really need it? Or are you going to drop it in a bucket of water?
they say it's waterproof. It's got
okay. Good.
So that's not terrible.
The only thing to think about, and this could be with the other eyepiece too, does this one have a sweet spot, or is it or is it okay,
edge to edge? Yeah.
Well, do people have to accurately put their eyes in the right place, otherwise they don't see anything? It's like the old Nagler. Naglers had that kidney bean type thing because they needed to be you needed to send your eye really really well. Yeah. That was on the first ones.
They both have eye relief. I think this is 14.5 for the Explorer Scientific, and the eye relief on this one was 15mm eye relief, 2-inch.
Okay, so they're about equivalent.
9 elements, 9 elements. Doesn't say how many elements here. Teleview, I wonder what Teleview has for 100. Do you have a 100-degree?
It's called the Ethos.
Ethos, 20mm. So let's see what and Teleview them have it right there. Let's see. I'll try this.
Okay, I think for the longer focal lengths, it's 100 degrees, and for the shorter one, it's just 110, I bet.
Yeah. Yeah, they have the price. They don't have their prices listed right there. Oh no, I guess not. Let me try
if you
someplace.
Have to ask, you better. You can't afford it.
Cloudy Nights. So why are Teleview's Ethos better than Explorer Scientific? Let's see. I'm about to spend a little over $2,000 to buy a set of 4 eyepieces across Teleview's Ethos line in the process. This is 2017. Made in China. Find difficult to explore. Also made in China. Debating the merits. And let's see what people say here. Why don't you call Mr. Nagler and let him answer himself? They're made in Taiwan. This guy says Taiwan. And all glass comes from Japan. Oh, really? All the glass comes from Japan, the guy says here. Ethos are better corrected than the Explorer Scientific. You want the best glass, you're going to have to pay for it.
Yeah, with your kid's inheritance.
Yeah, resale value is kind of like buying a Honda versus a Ford. The resale is just credible. I don't know why, because we've had trouble with our Honda, with our Toyota, and somehow the resale keeps staying up there.
Yeah, perceptions.
Yeah, it's amazing. I guess, maybe overall the mileage you get off those Honda Toyota is much better than the American ones. That's why they get it. But we've been happy with our American cars. All right. Well, it didn't say about price wise.
I just sunk one or 200 into my Yukon XL just for a new emergency brake cable and check everything else, and so that wasn't out of the line.
What year?
2002, and they say that those vehicles are good for approximately 400,000 miles, the engine.
Wow, really? The GM Yukon 2002. Yeah. Wow. Is that the same as Suburban?
Yeah, they're very similar.
Very similar. That's amazing. Yeah, well,
Yeah.
Bruce likes his Suburban, taking things around.
Yeah, I
So
get
Ju-
halfway decent mileage with it too. I get about 17 on the road, which is nothing to sneeze at when you're hauling
Jer-
a bunch of junk.
Jerry, we were just talking about, I just bought a $250 100-degree eyepiece. It hasn't come in yet. It's on the way kind of thing. So it's ahead of time. Astrotech 20 millimeter from Astronomics. This is their brand. And comparing it to the Explore Scientific at 800 and the Teleview at 890.
Mhm.
And so it'll be interesting to see how well, how many elements in this one do they have here?
Well, if you're not too critical about things, it's probably okay. I mean, when you use an eyepiece like that, it's basically where did it go type of thing with a Dobsonian, where you need to move it around, you know.
Well, this is a wide field of view. You're gonna have not so much trouble tracking, I don't think.
Right.
Almost an inch.
So that's,
But that Teleview one, I mean, that weighs a couple of pounds or something.
yeah, this one's a little bit lighter. It's a little less than 2 pounds, like 29 ounces on this one. The Explore Scientific and the Teleview are both over 2 pounds.
I think there's over a dozen elements in the Teleview one.
Wow. Plus really special coatings probably.
I sent a number of people in the club a history of eyepieces
Yeah.
a while ago, and it shows the lens layout of the Nogler, not the Ethos, but the Nogler type of eyepiece.
Uh-huh.
And the Ethos has more. I'm sure you can find it on the net somewhere.
Yeah. Anyway,
But it
so
looks
that's,
like an eyepiece. Would go back to it, 250.
yeah, it's so, and this is a whole range of their eyepieces. The come on, where's eyepieces? Their Astrotech,
Go up, up.
WXY,
Okay.
and they're all, they're just coming in. So it's
They're all
something
250.
they're all 250 for the whole range. I had a 9 and a 14 from Explore Scientific, so I thought I'd go for a 20. And yeah, so their retail is going to be 280 or 300 over there. So I'm getting 250s. That's even a better deal. So I thought I'd go for it. Don't really need it, but I thought it was one of the ones I kind of wanted, the 20 millimeter 100 degree. Love the 100 degrees on Dobsonian, for moving things around.
Mm-hmm.
Yeah, I've got, all I have is some Pentax X LWs, they're only 72 degrees, but
LW, what's LW?
they're Pentax.
They're what?
Pentax.
Syntex?
Pentax.
Oh, Pentax.
Yeah.
Oh, yeah. Yeah.
They are very trouble-free as far as where you stick
I've
your
heard
eye,
great
you're going to see
reviews
some.
about those. They're supposed to be excellent eyepieces.
Yeah, I've got 3. I've got like, what is it? A 40, which I can't use anymore because of my short focal length scopes.
Uh-huh.
A 20, a 14, and a 10.
Mm-hmm. That's a good range.
Let's see. So what's the field degree?
They're 72 degrees.
They're 72.
Something
It shows
like that.
61 to 70 here. Pentax.
Well, those are XWs. Those are different. Those are more towards the planetary type
Inch
stuff.
and a quarter. They're only 1.25 inch eyepieces.
Yeah.
Here. Let's see. How do you find a different one? Let's see, a 2-inch. Here's a 2-inch, 40 millimeter 2-inch. That's what I want.
Yeah.
$400.
But they're not the same, they're 70 degrees. I stand corrected.
Yeah, 70.
Yeah, it says 70 degrees.
Yeah.
Well, it's better than Apostle or, and they give good images and they're very easy to use. I mean, you don't have to be super accurate about where you place your eye,
Eyepiece.
retractable eye cap that's built in, permanent.
What was this? 100 degree.
Well, I guess the
Yeah.
Teleview, that's been out about 15 years. And the price has never wavered once.
Seemed like Teleview had a sale once a year. Oh no, I think that was Explore Scientific. Yeah.
Teleview does have a sale every now and then. They take like 10 cents off the price or something.
Yeah.
Wait, there was one out at the bottom that's $1,000. I've never heard of one like that.
Oh, yeah.
25
long
millimeter, 100.
Oh.
That's Explore Scientific.
No, down more. Down.
Oh yeah, Explore Scientific,
Yeah.
30 millimeter. Supply and demand, I guess.
It's
big heavy-
probably a lot of glass.
Oh, that's a 3-inch eyepiece.
Oh,
Yeah. So I mean let's see how much this thing weighs.
Probably
Let's
4
see.
pounds.
Tech details, 5.2 pounds.
Oh, I was close.
now Gary Peterson has one of those heavy eyepieces, not the Teleview for $890, but the eyepiece is so heavy compared to his other eyepieces that he has a solid brass plug that he bought that the lighter eyepieces fit into, so there's not a big weight change when he moves from one piece to the other. So his Dobsonian stays balanced.
I bought some magnets to put on my big, 1 pound magnets to put on into my Dobsonian to help balance things out if I put a big eyepiece on.
Now you just got to be careful with those magnets. I don't allow anything around my electronics that's magnetized. It'll completely erase your discs and your thumb drives and really screw up your camera.
You think it affects a memory card?
Oh, absolutely.
Solid state? Mike,
Yeah.
is that true,
Yeah,
Mike?
of course.
I haven't heard of it, but that's not to say that it's not true. Some memory cards use magnetic memory inside, ferromagnetic.
Bubble memory.
Yeah.
No, not bubble memory, ferromagnetic. It's similar to a EEPROM in a way. And they use it, a lot of them use it for storing parameters, operational parameters, not normal data, because it's they don't make too much of it.
Mhm.
Well, I got some news, some good
Yeah,
news in the
go
way.
ahead. Yeah.
I just got an email from nexdome after I kind of waited a couple weeks and says, hey, are you shipping me my parts that you're supposed to replace? And they said, we're getting it ready for shipment. Okay, so I'm getting replacements, parts for the nexdome. The other thing too is I'm getting more accuracy with the bath interferometer. And I'm learning a lot of things. I'm sending things back to George. He's going, no, you're doing it wrong, but I'm getting more repeatability and some of the things that can, like, some things that aren't really spelled out quite well, they all know. And so they, in a way, they need to update their wiki or their help. But one of the things that I got to work on is get better focus with the camera, not with the bath interferometer. And he showed me where I was getting ears on the igrams. And he said, oh, for what you're doing, just getting 1 or 2 igrams is sufficient. You don't need to go to 20 or 30. Yeah. So one of the things I got to work on is better contrast. And he said also, it seemed like the mirror igram was not centered well enough within the, they call it the reference beam, which is the beam that gets sprayed out with a spreading lens on the mirror.
Mhm.
It comes back and gets zoned. And he said, also your reference beam seems to be a little bit low in amplitude, but I didn't tell him that I used a polarizer to reduce that into the camera, figuring that it wasn't necessary, because he was talking about reducing that. But so I noticed that my lines aren't quite as sharp as his. Let me see here. Let's go exit full screen, and let's see if I can get a report to show you. And I sent him different reports. He said, yeah, it looks like you got about your mirror is about Strehl 0.8 or a little bit better, and that's that's pretty good,
Uh-huh.
and that okay, now I'm trying to find my reports here. Okay. Oh, I know where they are. It's under bath.
Pretty sneaky.
Well, I don't, oh, shoot. I got to find out which bath it is. It's one of those things where. But I can.
While you're doing that, just wanted to, I'll show this eyepieces for sale on cloudy nights. Oh, those are all sold. Okay. I thought I saw a couple that weren't sold yet, but no, they were under a couple $100, and they're William Optics 20 degree and
Mhm.
it's Mead 20. Yeah, they're
Someone
sold
that makes
already.
one that's over 100 degrees, 120 degrees or something.
Can your eyes really, see that well?
Yeah, if you look at it in the teleview, what are those called? Ethos. In those eyepieces, if I look in there, I can actually see the entire perimeter at once.
Huh.
I have excellent peripheral vision.
Well, so does my mom, but she doesn't have any regular vision.
Regular, it's all peripheral.
It's all peripheral now. Yeah, and that's a kind of a shame. Here I'm trying to find. Oh,
But it's kind of fun. The wide field of views. You just kind of fall in there, and you kind of look around.
Yeah,
It's kind of neat.
it's like you're looking in a picture window out into space. It's very nice. Gives a nice effect.
okay. Hold a second here. Okay, where did it go? Okay.
How's our weather looking? Looks like Thursday might be worth looking at the sky.
I don't know. I don't have anything to look at it with or from. My patio is still all discombobulated. My telescope's in process.
What's your timing for getting things done?
Oh, we were assured they'd end date would be December 10. So we're working to that.
Oh, this year, last year, right?
Last year, yeah. So the actually they're not doing bad. They right now we've had just one person show up a couple times a week. The rest of the crews have all got COVID. So,
yeah, I've got relatives that have COVID now too.
That
yeah.
happened. That happened to our plumbers a couple weeks ago. They're coming in tomorrow.
Mhm.
You find it, Mike?
Not really. I'm coming up with something to show you.
Here's a moon by Astrobin, somebody on Astrobin, and then I'll show you Jurgen's cell phone moon. Let's see. It would be nice to be able to do them side by side. So Jurgen's is this one here. He took that with the cell phone on his 2-inch unitron. Is a 2-inch unitron telescope, 900 millimeter focal length.
2.4 inch.
Oh, 2.4,
Yeah.
and then a 10.5 millimeter eyepiece that he was looking through.
Uh-huh.
Not bad, not
No,
bad.
that is nice image.
Yeah.
Those televiews are f/16, f/15, so they give really sharp performance. Complete color free.
Full moon is hard to take. I don't know if you use any filters or because it's hard to get some of the bright areas. It seems like that's good. Depth of field, not depth of field, but
Dynamic range.
dynamic range. Yeah.
Big contrast.
Yeah, it seemed
I'm sure
pretty
he's
darn,
processed it a little bit.
pretty
It
good.
could be just exposure time that brings the contrast up too.
I mean, what a longer or shorter?
No, in a bright object, you cut down the exposure time to unsaturate things. It brings
Right.
out more detail.
Yeah, I generally try to underexpose, and then you can bring the shadows out. You can't
Right.
once you overexpose, you can't bring that back. Yeah.
That's right.
Find it, Mike?
I'm still trying to, sorry. I just keep talking.
Jurgen says he watches our shows, so this is for you, Jurgen. We're doing it for you. When I post this later on, since we're not live.
Well, here, let me just show you something here. Well, second, I gotta go. Okay, so this is where I'm getting into problems with the ear and all that, where he says that I need to have more uniformity from top to bottom. But anyways, I think I also need to be better focused on the mirror edge. Okay, so there's two focuses you have to worry about. One is what the BAP determines to be the focal point to generate all its surface data from, and the other is the camera that generates the I-gram, and that needs to be focused exactly on the edge of the mirror, and then it builds it up from there. Because what they recommend is f1.8 lenses, or a fast lens, because with a higher focal ratio lens, you have a tendency to vignette the image.
What's the focal ratio of your camera lens?
Well, I've got a 85 millimeter f1.8 lens on my camera.
Wow.
I paid good bucks for it a while
Yeah,
back. Yeah. But hey, it works for the 5D as well as it did for the 40D. So it wasn't like I was going to go put it in the trash can when the 40D went south.
I'm surprised that 85 isn't maybe a little bit too long for zooming
Yeah.
in or something, but
Yeah. Now, one of the things that the DFTFringe does is shows you the point spread function. So what I did was I generated a background for the Webb telescope, and I asked Richard Berry, how do I go about getting a point spread function with this? Because I expect the point spread function of this to be different than a regular circular telescope. It'll be similar, but not exact. You get spikes and other things. Am I wrong, Jerry, or not?
Well, the point spread function is a function of course, of the aperture shape, but it's also primarily a function of the correction of the optic.
That's true, but we're talking about a perfect, let's say, parabola versus a perfect refractor versus a perfect Webb telescope,
Mm-hmm.
because you're going to get different diffraction spikes and maybe,
Well,
and
if they're perfect, then your point spread function is going to be the circular diffraction rings of a, what is it, diffraction limited optic.
right. So, yeah. Anyways, so you don't think it's going to make that much of a difference? Okay.
Well, what exactly you with that pronoun in there, it, what is it that's not going to make a lot of difference? The shape of the aperture?
No, the airy disk is going to look similar, you're implying.
If anything is, if it's perfectly corrected and it's a circular aperture, you'll get the classic concentric diffraction rings.
But this is not circular. This is sort of like jaggles.
Jaggles, I don't understand what jaggles are.
Well, look at the Webb telescope. It is not a circular mirror. It is.
Oh, you're talking about the James Webb, yeah. No, there will be.
Do I have it up on the screen?
Yeah, you do. I wasn't
Okay.
looking at it. I was looking
Okay.
at your smiling face. So I have a big screen. I have to go back and forth to.
And all my feelings.
Yeah. So yes, the aperture, the shape of the aperture there will have an effect on the patterns. It will. So if you look at the things when for example, the I think it was either the Palomar or the Mount Wilson telescope for the first time put a extra wings on the front of the thing, and they made it an interferometer out of the telescope, and it had the effective aperture in one dimension of a much bigger telescope. The actual image there was a series of vertical lines. So that's the effect of that one dimension. You see, in one dimension it had increased resolution, and the other didn't. And you're going to see a little of that in any non-circular aperture. Yes, you're right.
Yeah, I just wanted to show this is from my meeting where I'm trying to entice people by saying, what does the Webb telescope and Chinese takeout have in common? I was trying to get more people to go to the meeting. It's origami. So I wanted to show this, and when you look at
I think
the DFT,
origami is Japanese, not Chinese, but that's another
yeah,
story.
that's true. Yeah, I know, but
Okay.
but I'm talking about the container,
Yeah.
Anyways, I was thinking, you're talking about vertical lines, you're right. And I'm wondering about like other telescopes like the Gemini, what it probably showed. And also
What was the
something as
Gemini?
strange. What?
What was the Gemini?
The Gemini is those 7 circular big mirrors, the giant Magellan telescope. Is that what
Okay.
yeah. Oh, well, yeah, you're right, though. The Gemini telescope out on Hawaii is made up like the James Webb. It's a bunch of hexagons, but it's a lot of them.
Yeah.
Yeah.
So, I'm also thinking like the Chira telescope over at Mount Wilson.
Uh-huh.
Okay, that is technically a single telescope made out of pieces that are separated by, hundreds of feet. And, to tell you the truth, they haven't shown us any images to the general public because maybe they're not happy the way they
Still
look.
trying to figure it out.
Yeah. So, I was looking at DFTFringe and figuring, well, maybe I could do that because they got keep out zone type stuff, but I could just see that I could not do that, with a figure like this. It'd just be impossible. It's not made for that. It's just made for keep, circling things and saying you're not getting looked at. And so my second thought was, well, I'll go make a cutout of this and put it in front of my mirror, and I'll know what happens. it'll cause DFTFringe to blow up, because anytime you don't have a proper edge, you'll get these big ears. So the only way is some sort of program that
So
simulates.
if you use this bath interferometer on a mirror that you're testing, but the mirror is held on the tester by clips around the edge of the mirror, will that break up the pattern?
It could, and there's a tool there that you draw around it to get rid of those. So to tell, ignore this, ignore your center.
Okay.
And it'll
So how do you mount your mirror? Is it held up the usual way with a rubber band across the face?
no, I have something that kind of grabs in front. Okay, normally.
Okay.
And when I
Gotcha.
take my interferometers, I move it up because it's,
So you're tipping the mirror. So gravity holds the mirror in place.
well, this is the 10-inch mirror, so you
Yeah.
know it's going to stay there. It's on dowels, okay, so it's not going to move. The 14.5-inch, I'll have to figure that out. Probably it'll be like a pin or something like that, small. But if it isn't too big, it doesn't affect it. But this here with the Webb telescope is significant. You know,
Mhm.
you got the jaggles, and I'm wondering if some smart folk have figured out, well, hey, I could use this to my advantage to start, you know, the way the diffractions are, that let's look at the null and see if we can see an exoplanet directly. You know, that might be part of the reason why they it's not as circular as it could be. You know, it's
Mhm.
Are you still talking about the James Webb?
yeah, the James Webb, yeah.
So,
Because
so
it's
what?
going to have an interesting diffraction pattern at a point spread function with it, and it might have some good nulls to do some searching around planets.
Here, let me
Maybe.
show
maybe.
you something here. I'm gonna share screen.
Okay, I'm going to stop share,
Okay.
and maybe.
All right. And here's something on the James Webb. And I was looking for a point spread function, and talks about the Strehl ratio. The point spread function metrics specified for JWST are the following: Strehl ratio, encircled energy fraction. They do that twice. I don't know why.
Do they have any illustrations in this article?
Yeah. So down further here, that's a primary, secondary. They showed something like this.
Yeah, keep going.
Is this
You
it
want
here?
a picture? Nope. No, that's not good enough. Keep going.
This one Strehl contribution.
Keep
Yeah, that's
going.
real calculations there.
Okay.
Don't know if they're going to give us any images.
Let me share one with you.
Okay.
So there's the pupil of a hexagonal composite mirror, and there's the corresponding point spread function for it.
Does that mean they measure at all these different points and average them together?
I don't know what you mean.
Just,
This is what you will see. This replaces the circular diffraction disk of a circular aperture, but because of all the segments and the edge, you get these points which actually show up as bright spots, and you get these rings.
It's too bad they don't have. It's too bad they don't have Fuller. Otherwise, we'd have the Webb telescope there.
Yeah, that's the central part. That's the airy disk corresponding.
Yeah, so it probably affects the outlying rings rather than the central disk.
These are classical from
yes,
secondary mirrors with spiders, curved spiders was earlier, and now this is typical spiders that we're familiar with.
Yeah. You know, it seems to me that the best spider is probably the straight spider that's the thinnest. Otherwise, you're adding more area to the, in front of the mirror.
Yeah. Well, the best spider is a glass window with the secondary glued on it. And
Yeah.
then after that, I think it's a single vein spider.
And that's,
Go ahead.
that's going to be one of my projects. I do have an 8-inch optical window for a missile tracker from Point Magoo. That was basically a Cassegrain, but with a flat secondary. So I'm thinking about making an 8-inch superplanetary reflector. One of my various mini projects.
Am I still sharing?
You are still sharing.
I wonder what happened to it. Okay.
You are viewing Jerry's screen.
There it is. Yeah, I just wanted to show you where I got that article. So this is from Proceedings of SPIE, SPIE, Society of Professional Industrial Engineers, International Engineering, something like that. But I don't see the time.
Go to page 1.
No, I don't see the.
Talking about the date that it was written?
Yeah, there it is, 2018.
I don't see it on the
Okay.
screen.
Yeah.
But that's good enough to show that,
Okay.
that's good enough to show that in a way they're going to get what they want. It's just the secondary stuff is going to be a little strange.
Yeah. You probably won't even notice that pattern. This is, of course, way blowing up the resolution element very much. Oh, I lost that train of thought. Okay, go ahead.
Now leaving track 9. Anyways, so if I get the chance, I'm going to take some more 10-inch interferometry stuff. I'm saving all the emails for you, Jerry. We'll tie them in a nice big bow there, because I don't expect you to do as many stupid mistakes as I did, but we could all,
Well, I'm putting the laser and the lens on my bath interferometry, and then I'm starting to look at how to mount my 18-inch mirror, which I want to look at. But I'll probably start with a smaller mirror first. So
Yeah,
I don't think I have any dynamic or any lenses that are f1.4. That's pretty fast. That's what we used to have with film.
Well, you got a normal lens?
Well, I use a subframe chip, like the 60D camera. So it's not a full frame chip. So the standard lens is a different lens than the standard lens from 35mm photography.
But just try it.
About 28mm. I think I have a 28, but it's a zoom, 28 zoom.
That might work.
I have a macro lens, but it's not that fast.
You'll find the reason for a wide lens is so that you can take it further away from the bath tester, because the light spreads out from the back of the splitter.
Okay.
So you might be able to get away with it. I know that I tried with my 1.885, and I could stop it down a couple stops, but it was getting kind of close to where it was falling off. So you probably have a better situation where you can move the camera in finer motion slowly.
Okay.
What are they showing here for the red lines and the blue lines? What are they showing?
The red lines, I think, are the red lines are, I think, the reference, and the blue lines is the other one, the the test, I think. And so the reference gets bounced by the splitter, goes through the lens and gets spread out across the mirror. And the same time, with the flat mirror on the bottom, you've got the other beam that goes out that's narrow, and that they both come back, and they it comes back on the flat mirror, gets bounced to the camera. So
the splitter.
Yeah. So it looks like the reference goes out through the lens, but the test data goes through the lens, back through the lens itself, the way he's got it shown.
So the blue is going out to your mirror, and the red is coming back from your mirror.
Yeah. No, well, no. In the on the upper with a lens, it says the blue is going into the.
Yeah, that's a little confusing.
Yeah, it is. Maybe it's
when
not
you
right.
start when you start with the laser, you see there's a red and a blue arrow superimposed.
That's right.
And the first time in the beam splitter, the red gets split off,
and goes through the
for the mirror.
Goes through the reference lens.
But not that way. Right there, straight out. It goes to the mirror. The arrows on the red go to the mirror. And then that beam comes back. It has to come back as the blue.
Yeah.
Oh, it comes back as blue, you think, not as red?
I don't know. That's what's confusing on me. See, if you go to an optical element that has power, like your primary mirror does, then the light goes out in a straight beam, cannot come back in a straight beam. It has to be refocused somehow. So the blue can't go out straight and come back straight.
Well, the blue is a point source as opposed to a spread out circle with the reference beam, which is red. So it probably does get spread out, but it's infinitely small compared to the other one. I wouldn't.
That's not clear to me. I'll have to give that a better look.
Yeah. Anyways, seems to work.
Yes.
So I was getting variations, on a specific run. The Strehl was changing like less than 0.01. No, not 0.01, about 0.02. With one being the Strehl of 1. So a few percent, and then from one run to another, it's around 0.8 to 0.8 something, a reasonably good mirror. And what all of them show is the fact that I have a high spot, a high ridge. Okay, let me go down here, see if I can. I don't know where in the heck the things went, but let me, something happened here. Okay, let me just go and get a Strehl here. Okay, let me just hold a second here before anything else happens. Let me do a share screen. Okay, so we got DFTFringe. Okay, hopefully this one isn't too sucky. And so I need to add zoom.
That one looks like a pretty good pattern.
No, it's okay. He told me, see that fuzz there?
Yeah.
That causes ears and stuff like that. Whoops. Let me just undo it again.
So where do you get that fuzz from?
My camera.
It's not from your mirror?
No, he says it's has to do with focusing.
Oh. Okay.
Okay, so some of the newer images next week that you guys will be seeing probably will be looking a lot better. Okay, so it's done. Okay, there's my,
Why is it black and white? Shades of
it's
gray.
just, it just shows intensity of your DFT. Hopefully this isn't a crappy one. Yeah, it is a crappy one. So you can see where, you know, I've got these big ears coming out.
Uh-huh.
Okay. So let's go find another one that's not so bad.
What is this? What is your program called there? The one that does that?
DFTFringe.
Oh yeah.
Okay, let's see what that does. Yeah, okay, so you can see how it shifted because the lines are, the diagram is shifted. Okay, the other one was back and forth. This one's at a 45-degree. So when you're looking at this here, the distance between this central spot and this spot and this spot and this spot has to do with the number of fringes. Okay, the rotation has to do with the rotation of the thing there and intensity graph. Okay, so this here is sort of like the intensity of the fringes.
Mm-hmm.
So that's about right. Okay, done. Compute surface. Seems inverted. Okay, this might look pretty good. It's still got a crap in it. Okay, so Strehl's 0.579. Let's do something here. Let's go to 20%. Get rid of that nasty thing. Well, it's still there. But it does say the Strehl is 0.7. Let's go do something nasty here. Mirror. I'll mask off a slight amount. Okay, recompute. Okay, it's much better. Okay, so when we go to the profile, the wavefront error, okay, which is this bottom one here. Let's see if I can move this up.
Mm-hmm.
And okay, so from here to here is an 1/8 wavelength of light. Okay, so that's telling me, and on most of this, it's pretty much there. I've got let's try some here. I want to. This is not allowing me to do it, but full screen. Okay, there we go. Anyways,
Mm-hmm.
so this is 100%. So as you remember on my 10-inch telescope, I had a rolled image. So this here, I think it's just imaginary type stuff that's happening. Maybe probably due to the smoothing of the filter. But this is pretty consistent here. So that says it's about 87%. I have a rise here. And so he said, if I really wanted a truly great mirror, work on this and get it flat. So you can see here.
So you need to turn down the edge.
What?
You need to turn down the edge then.
This is not, it's just before the edge.
Yeah, okay.
So what I should do, stop share. I wonder if I can find my old data that we took for my original mirrors. Let me look. Desktop development files, mirror making, 10-inch mirror. I don't know if I have got lots of pictures, but I don't necessarily have. No, I can't find the report. All I know is that when we all seem to have a bit of an issue of really seeing the, the nitty gritty of a mirror, when we're doing the Foucault tester. There's always sort of like, I remember there's a little disagreement between you and Tom and all that, as to exactly where it was, and if the plane, the optical plane and the mechanical plane of the Foucault tester isn't right as you go in and out, you have to shift things back and forth, laterally. And I think that can introduce some error.
Yeah,
So,
you're right.
So this might be a boon to us because it probably takes that out of the equation.
Oh, yeah.
So, but I wish I could have found the, it looks like probably what I did was I did so much housekeeping on this computer that it got lost. But, but I remember that it looked okay, and we could move the curve up and down to where it looked halfway decent, going, that's good, let's see here. Anyways, you got anything new with you guys?
No,
So Mike, I wanted to ask you on that interferometer, the image that you get on your camera, what was that image that you feed into the program? What does that look
It's
like?
DFTFringe.
No, but the actual, I think you showed it. Which one was it? The camera, the image that you get off your camera that you're feeding into the program?
Well, what I actually was using, and I don't think any of the interferometry people use, I use Backyard EOS to take my images, in a sequence and adjust the focus and all that. Okay, so I guess you get a bunch of JPEGs. This can handle JPEGs, and then you just download the. What you see is what it thinks that the JPEG looks like. It goes through a little bit of pre-processing before it does anything, and you get that black and white image. If I were to go in here,
Yeah, I thought you showed what's
yeah,
getting fed
to
in.
answer Tom's
here's-
question,
here's-
it's just
here's-
those fringes.
Yeah, here's the igram. Let's see here, show color channels. Okay, so here's my color channels here. Okay, oh, I didn't share yet. Let me go share. Okay, so if we go to show color this is what it sees. The three different color channels. And so I chose the blue because that seemed to be the brightest. If you go to the show intensity, you can see here at the top there, the red is basically saturated. Now there's something that I think I can help things with my camera, and so can you, Jerry, is to get rid of the gamma correction inside your camera. He says that causes issues with this. So just something to keep in mind if
You're saying it's really a processed image that you put into your program.
yeah, you don't want your camera to pre-process the image to make, there's a gamma function in there that's used to keep the camera from whitewashing super. Yes. Okay, you take that out, you get better interferometer, igrams, I should say.
Okay.
So
does a fringe program, does it take in the raw images or just a JPEG?
It takes in JPEG, and I forgot what the other one. No, it doesn't take in load interferometer. Okay, and let's see. I'm going to go down here. It'll look at TIFF, GIF, PBM, GBM, TGA, XBM, but nothing in the form of a.
Well, you could probably
image.
use a raw image and convert it to a TIFF or something. And that'd
Yeah,
be-
you could, but
Yeah.
why would you if it could take a JPEG? As long as you don't pre-process too much.
JPEGs are inherently processed. You know,
Okay.
it's a data compression program.
So what is it? A raw one, you'll give you like 16-bit color versus a JPEG would only be 12-bit or something, or?
Okay, well then I suppose what I could do is go, it likes a TIFF or a GIF.
Uh-huh.
Those might be a little bit better, but my camera does, I don't think Backyard EOS saves it as that. So I'd have to go through something like this program, which is Faststone or something like that, where you do a batch processing. The reason why I chose JPEG, because what I could do was I'm controlling.
George said JPEG works, right?
Yep.
Yeah. So then why worry about anything else?
Yeah. Well, another thing too is that's true. But what I was going to say is with Backyard EOS or Backyard Nikon or whatever, or a program like that, you can see in live view exactly what the camera's seeing and maybe focus it a little bit better. And then what you could do is take some test exposures such that if we were to, okay, if you really wanted to use the red, you could lower it to the point where you're getting decent reds. You know what I mean? And Backyard EOS would allow you to do that. So what I was doing in some of these runs was I was using Backyard EOS to find the first couple of shots, okay? And I would bring it in and I would first get the outline of it, okay, as best as possible. Go into what, look at the results, possibly look at the star test. Actually, it doesn't look too bad, does it? Where is it? Yeah, it could be better. And then once I got that ready, I would go back in the Backyard EOS and take a bunch of different pictures at different exposures, and just let it run. Because one of the things that you don't want to do is once you take the first image, you don't want to touch the camera at all. And so let that run. In the meanwhile, with Backyard EOS, you're able to give a unique name for each orientation of the interferometer in the interferograms. So you know what you have. So when you bring them in, you can tell, these were done. This might say this at the 10 o'clock. So you got the 4 o'clock, the 2 o'clock, and the 7 o'clock bands. And you want to do that. You want to average them, then get the average of each of those clocks, okay, and then average them all together to get the final one. And that allows you to get a more reliable interferogram. So if I were to take a look, let me just go back to share again.
So you just can't come up to your mirror with one shot and get it, huh?
You can, but you have to be lucky and things have to go right. And if you want to know for sure, then you want to do this. But going back down here, the Zernike values here. Okay, I had a defocus of this. He says that's very good. A lot of people, this shows the focus that building the surface relies on. It's not the camera, it's the building. You want to get that as low as possible, close to zero. Now, it's kind of interesting. The tilt is the tilt and the other ones are not used, but they calculate it because this is what they talk about as far as counting the number of fringes from the center one way and counting the fringes to the other way. And they use that as part of building up the surface. So you never have these checked. Piston is focus. Tilt is, again, not used. Defocus is what if you don't have it properly focused, and you can see the point spread function change. So I was a little off, but not enough to really make anything. In this case here, the astigmatism is not too bad according to him. But this is what you really look at, is your spherical aberration. So this is sort of like the overall spherical aberration. And one of the things he reminded me of, go look at your second spherical aberration. Okay, so if we go back to our results, and if I can get back to, I want to go and take a look, view my contour. No, not my contour, view. Okay, I'm going to get this right one of these days. Which is the one that's down there? View. Okay, I'm kind of at a loss here because I know that, oh, hold a second, this, okay. What was I going to say? Trying to find this, I lost my train of thought.
Must have been track 10.
Yeah, right. Leaving for Burbank and Cucamonga. Oh, this here. Yes, back to here. I now know what I want to talk about. Okay, so your general curve here, a spherical aberration, is going to look something like this. This implies what I've done is I pushed out here, pushed this down, this got pushed up. And so
I don't think I can see your mouse if you're pointing at something.
okay, right here, it's an X.
There's no
Okay, it's at the 90% point. Can you see the surface smoothing diameter? It's sort of a wave.
There's no cursor we can see. If
Okay, hold a second here. Okay, share. Okay, can you see it now?
Yes.
Yes.
Okay. So here's the peak. So what MikeC did was MikeC tried to get rid of his turned edge. And so this should have been smoother. And so what I did was I pushed down on here and pushed this up. And that gave me my secondary spherical aberration. So if we go back to here, can you see this now? The other screen? Okay, I guess I'm going to have to stop share and do another share. Okay, we learned. Okay, the secondary spherical aberration, according to him, and third, is indicative of not making a nice, in other words, having a zone of sorts, because it is a zone, or we have a donut. It's like got a raised zone. Okay, so this will tell me general characteristics of the zone. If I had pure spherical aberration, those other ones wouldn't be seen. So, so that's something more that I'm kind of learning about, because I'm not a total optical geek. Okay, so if I were to unclick the third and the second and do a recompute, it should change it a little bit. See? It moved it out. Okay, so, and if I were to enable spherical aberration only, this is what it looks like. So it says that if it wasn't for those secondary stuff, my spherical aberration would be, Strehl would have been 8.29. Okay, so what I got to do is work on this area here if I wanted to. bring that down. We're not talking about much of a hill, you know. We're talking, you know, probably half of that probably brings it into proper range. You know, a 10th wavelength, maybe, you know.
That's only about once or twice around the barrel at most.
Yes.
Provided you get the tool bearing right on that region.
Right.
It's going to go very quickly.
Oh yeah. In other words, you know, I was almost there. It's just that, you know, with the horn of optical plenty, so to speak, the French guy, I have a terrible guy thing with names, but anyways, that's pretty hard to see.
Yeah.
On a Foucault-gram, because
my experience with this is a little different than what exactly you were talking about, but my experience with camera lenses is that very fast lenses like f1.4 and f1.2, they don't give very good images except right in dead center.
And that's part of my problem. He said I wasn't dead center. That was another one too.
Okay.
Yeah. So I could stop down, get it better centered, make sure that I'm really got the edge of the mirror in sharp focus.
Right.
Because it needs to be, that I could get better images. But hey, look, you know, we're around 0.8. And according to him, on most nights, you're not going to see it, you know, on most objects. You'll see it on planets. Okay, you'll say, well, it's a crappy night. Or you know, the difference between, I guess, a crappy night and a crappy mirror is not all that much, I guess. Okay, on a good night with a good mirror, you definitely see things. But
so Mike, on you're using your camera for these interferometer grams, are you setting a gain at, like, you know, I mean, ISO gain at low as you can, and
fairly low, because it's believe it or not, even though your eyes doesn't think it's very bright, it's super bright. It's really hard on the camera. So what I did do with that, what he did send with me with my new laser was a variable potentiometer. So I was able to, first of all, with the f1.8, I had to go set my shutter to the fastest speed, which is like 1/4000th of a second. And, you know, it's still blasting away with a red light.
But you can turn down your ISO.
I did that too.
Okay. What were you setting at? 25?
A couple hundred.
Okay.
Okay. That gives me the most dynamic range on a camera, right? You go fairly low. But turning down the laser allows you to adjust the intensity of that too.
Yeah.
And so the one thing that I should do is get replace the knob with a dial knob, so that I can dial in a number. In other words, when I've got the proper intensity, I can set it to that number and remember that number. And so I won't have to you know, finagle around trying to get the perfect exposure. So ideally, you want the perfect exposure to be for the red light, I believe. So, you know, I'm having kind of fun with this, and it kind of tells.
How does that Strehl number relate to the whether you're like 1/8 wavelength or whatever you need?
Strehl is the amount of light that goes into the central spot of the light.
The airy disk.
What?
The airy disk.
Yeah, the airy disk, right. So the better the Strehl ratio, it becomes close. A perfect one would be 1.0. Okay, so mine's off by like 20%. But in the case of this one, you can see your modulation transfer function, that I'm not losing too much
No.
here up until I get to the medium resolution
Right.
data. So
Your
that might,
fine detail is performing better than the medium-sized detail.
right, which means for the moon,
Yeah.
I'm golden. But for the belts of Jupiter, maybe not. And I'm not sure about the festoons and stuff like that on Jupiter. It says that it's a reasonably good mirror.
Yeah,
Okay.
it's not
And
bad.
this is your 14-inch thin mirror, right?
No, this is
Oh.
my first mirror,
10-inch.
10-inch mirror.
Okay.
And like once around the barrel, I can make it a fantastic
Hmm.
mirror. But
Or
just leave it alone. Enjoy the damn thing. This is what happens when you get a tool that allows you to become nitpicky and miserable about the fact that you're not perfect.
Interesting.
Yeah.
Thanks, Mike, for all the detail there.
There's a tool of that in sociology. You know what it's called?
what?
Wife.
You're playing with dynamite there. Is she in the room?
No, thank God.
Okay, well, I'm going to have to sign off for the night.
Me too. Okay.
That's enough information for one night.
Okay.
Well,
I'll
thanks,
give a
guys.
report on my bath interferometry progress
Okay.
next week.
Cool.
Okay.
Okay,
All right.
Bye-bye.
Good night.
see ya.
Ending for all.